Welcome, everyone. This is the kickoff meeting of the joint Google-NASA seminar series. So we're going to have one of these things every 2 weeks, alternating between here and the Ames campus. We're really looking forward to the collaboration that will come out of that. Today we're going to have a tag team presentation, and Rupak Biswas is going to lead it off.
Well, I'm glad to be here. There's a lot of effort on both sides of the ditch or whatever you call to get this thing going. So again, I don't know what all of you are interested in specifically, so I'll keep it at a high level. And then as we go through the talk, and then maybe later during discussions, we can focus on certain specific areas. So I'm going to talk about high-end computing. High-end computing with the Colombia machine that we have at Ames. Even though the title says at NASA, I'm really going to talk about the Colombia stuff. And then feel free to interrupt me, or if you want to get into certain other areas, we can talk. I'll go for about half an hour or so. I'll give you an overview of what high-end computing is, the effort at NASA, and then I'll turn it over to to Chris Henze, who is going to talk more about the visualization. You'll see some of those visualization in the talk, but he'll talk more about the visualization techniques. So I'll start off by a very basic slide, because many of you, and if this goes to the next slide, of course, which basically tells you a little bit about how NASA is organized. Many of you may not know this, or if you do, then just sort of ignore this slide for a minute. So basically, NASA is a large federal agency. It's spread across the continent, and it basically has about 13 centers. 3 of these are research centers, so these are basic research centers like Ames, Langley, and Glenn. Some of these have very specific missions, like Johnson and Kennedy. There are other facilities that focus on certain areas, like Goddard is more into earth sciences. So this sort of gives you an idea that there is a challenge across the agency to trying to get all the high-end computing resources, or all of the expertise, or all of the vast resources and infrastructure that NASA has that is spread across the country. And at the bottom, there are these sort of thumbnail pictures that show you the various kinds of things that NASA is interested in, ranging all the way from aeronautics to earth sciences, space sciences, and exploration. I'll talk a little bit more about that. But this is how the various centers within the agency are organized. But the agency is also organized as mission directorates. And the next 2 slides, I'll give you an overview of what these 4 mission directorates are. And each of these centers sort of contribute to each of these mission directorates. Certain centers might be doing more in certain areas and less in others, but generally speaking, the focus of the various centers across the agency are sort of tied to all of these mission directorates. And I'm not going to read all of this, and you can read for yourself, but basically the 4 main areas, one of them is aeronautics. That is the core area that NASA has always been involved in, basically trying to identify the next generation of aerospace vehicles, airspace systems, for both space transportation, civil transport, as well as space transportation. Exploration is the big thing within NASA. In fact, this is exploration as a mission directorate, and then exploration as an agency mission. And the focus of this mission directorate is basically to sort of develop technologies for both long-duration space flight, both human and robotic. And as part of that, also to understand what the effect of long-duration flights are on human beings. So if you're going to go on a Mars mission, you're talking about a 3-year round trip. So how would such long-duration space flights affect human physiology? Science Mission Directorate is something that doesn't come out automatically out of the things that NASA does, but and it's broken up into 2 major parts. One is earth sciences, and the other is space sciences. Earth sciences, NASA is into that, and you would think that other agencies would be doing that. But because NASA is a space organization, it gives NASA a special perspective on Earth. So the fact that we fly outside of the Earth lets us do certain things about the Earth and science about the Earth that other agencies that are more sort of with their feet to the ground cannot do. And then, of course, there is space science. And then finally is the Space Operations Mission Directorate. This is the mission directorate that's mainly focused on human space flight. And right now, the 3 major areas are International Space Station, the Space Shuttle Program, and flight support. A lot of the work that is going on in this mission will sort of get evolved into more of this exploration vision and might get merged with with the Exploration Systems Mission Director. And then finally, there's this, across the agency, sort of a center called the NASA Engineering and Safety Center that was established in response to the Colombia accident to make sure that all procedures in terms of safety, as well as processes, as well as how scientists and engineers work within the agency, interact with the projects that come, do the reporting and all that sort of thing is sort of, you sort of try to break that dependency with that safety issues with the rest of the agency. So this gives you a little background, so that in case you don't know exactly how NASA is organized, it gives you a little detail about that. So let me now talk about high-end computing and specifically about Colombia. There are various things. There's sort of the stars were aligned in some sense that this happened. There are both external and internal factors. So some of the external factors, as you may know, was the Japanese Earth simulator. This is the fastest computer in the world for 2.5 years running. And it was the first time that any one computer actually held that #1 rank for such a long time. And the fact that, that the Japanese had actually talked about it and they actually were able to pull it off, it was not a surprise, it was not a secret. It took the US somewhat by surprise. And in response to that, the US government, among the various agencies, through the National Coordination Office, put together this high-end computing revitalization task force. The main idea was to understand how we could put the US back in the leadership position in high-end computing. There were other things that happened as well. There was a panel that was put together, and I was part of both the HEC RTF and this expert panel that went to Japan and tried to understand how the Japanese government was able to do this and how it worked with the Japanese industry, NEC in particular, because that's the machine that the Earth simulator is, and how they pulled this off. And then finally, as far as Colombia itself is concerned, there was, of course, interest from the vendor side as well. Intel and SGI particularly were very interested in playing a major role in putting together a system that would sort of put US in a leadership position. There were internal factors within NASA. Most of these are very NASA specific. So for example, the Colombia accident happened at about the same time, and then it was clear that high-end computing could play a major role in trying to understand why the accident happened and how we could prevent such accidents in the future. There were critical requirements for the next generation of modeling and simulation for space flight. And that we had a long history of working together with SGI, with this single system image, shared memory machines, and we had sort of established the success of such architectures as a viable platform for doing high productivity, high performance supercomputing. And the fact that before we had Colombia, all of NASA had a total capacity of about 6 teraflops. The system that we had at that time was about maybe 3 teraflops or so, and that machine would be completely overbooked just to do one mission, and NASA being a multi-mission agency, that was not acceptable. So I'll go through this slide real quick, but you have to understand also that NASA is not in the business of building machines. So we are sort of a mission agency. We're trying to get to Mars, get to Moon, get beyond, and all those kinds of things, try to understand where we are going, where we are from. And so it was imperative that there was some support and some partnerships. And I'll go through this real quick to give you an idea. So there's obviously partnership at the national level, and here you talk about the HEC RTF and that how the various agencies worked among themselves to sort of come up with a resource that was of national value. And as you may all sort of guess, that all architectures are not good for all sorts of applications, and there are at least 4 different architectures that are available at this time, and it was not possible for any one agency to sort of have large machines of a single architecture and be able to be experts in that architecture. And it worked out fine. For example, we at NASA were more into these shared memory systems. We had the Altics. Livermore went the Blue Gene route, so they have a big machine, which is right now the #1 machine in the world in terms of peak sustained performance on a benchmark. Oak Ridge was more interested in parallel vector systems. They went the Cray route. And then Sandia was more interested in clusters, and they have the AMD Octeron cluster. But with cooperation among the agencies, all of the major bases are covered, all of the major architectures are covered, and there could be sort of cooperation and trading cycles to sort of make sure that the right architectures were used for the right applications. But then, independent of that, you have to be able to, or we have to be able to satisfy NASA requirements. And NASA, as you can now understand, because of the various mission directorates, have very different requirements. Science, for example, is very interested in large computational power. They can really scale up their problems to any size they want. If you're doing earth sciences, you can make it a 10th of a degree, a 20th of a degree, a 1,000th of a degree, and you can keep going forever. However, there are also engineering requirements, and in engineering requirements, those are not quite the requirements because there are limits on how fine you can make an engineering instrument or a thing, for example. However, they are more interested in multiple scenarios. They are more interested in parameter studies, what-if scenarios. So they might be running hundreds of thousands of the same thing, but with different input conditions to see what the optimizations are and where the payoffs are. So that was also important. So we must have an architecture that sort of satisfied these diverse requirements. And then finally, like I said, it was really a sterling example of cooperation between government and industry. So Intel and SGI obviously were the prime partners. Intel provided all these chips, and I'll talk a little bit about that. SGI was the integrator. They put together these all-things boxes, these single system image 512 nodes, and then Mellanox and Voltaire sort of stepped in and did most of the interconnection and the InfiniBand and the fabric between these nodes. And then finally, when you talk about high-end computing, a lot of people have this sort of impression that we're talking about big machines sitting somewhere, crunching out numbers, doing floating point multiplications. But it's not that. It is an integrated environment. Anytime we talk about high-end computing, we're not talking about the system itself, but it's also the storage, it's the high-speed networks that go with it, but as well as the codes and the applications that run on that machine, and a complete sort of cast of support activities like post-processing, visualization, data analysis, code optimization, and all that sort of thing. And so that is when we talk about Colombia, this is the environment we are talking about. And that is kind of the environment that we have at NASA Ames. To sort of go on that a little further, this shows you an integrated support for this high-performance modeling and simulation. So we, as part of a supercomputing center, do not make the decisions what codes and applications need to be run. There are NASA scientists and engineers sitting across the agency at various places making their call as to what is important for the agency. They sort of work together with our computer scientists, experts on parallel programming models or data structures, as well as experts on the system side, people who know the all-things architecture, the Itanium platform, the interconnects, and make sure that those applications run efficiently on this machine. And like I said, it's not just the machine itself, it's the storage and the network. And then finally, all the results that come out, these are reams and reams of floating point numbers, get transferred over to the data analysis and visualization, and Chris Henze will talk a little bit about that, about the techniques that we use, and then turn those results over, the visualization, the analysis, the feature detection, and all that sort of thing back to the scientists and engineers so that they can either understand what the next step they need to do, what are the problems they have in the model or in the physics or the chemistry, and then sort of move forward. So this is how it all started. This is the building block of the Columbia system. This is the SGI all-things that we first had. It's called Kalpana in memory of astronaut Kalpana Chawla, who actually worked at NASA Ames in our division. And so this is the first SGI all-things. This is a 512 processor Intel Itanium 2 chip and a 1.5 gigahertz clock. This sort of gives you the specifics. This is how it started. Each of these, this is one node. So this is a single system image shared memory system. So basically all of the 512 processors can see all of the memory, all 1 terabyte of memory, and it had 20 terabytes of RAID, and it runs the Linux operating system. And so we took one of these and then we sort of replicated it 20 times. So that there is the picture of Columbia system. And some of you, I understand, are going to be at Ames tomorrow. So I'm sure you're coming over to the NAS building and you'll see Columbia. So this is 20 of those systems. Just to give you an idea, it has a peak performance of 62 teraflops. So if you can't do it in your head, then you can probably search on Google, or you can see what is read in the yellow box. So it tells you sort of, if you can multiply two floating point numbers every second, it would take 2 million years what Columbia can do in 1 second. The goal, of course, was not to build a system like this. You have to be, like I keep saying, that you have to be showing the impact on the missions, provide supercomputing and storage for the agency. The whole thing sort of was done in 4 months. That was a record in some sense, and it took pains from all sides, all parts of the government, as well as the industry partners, as well as OMB and Congress and everything, so that we were able to actually have this system up and running in 4 months. But it's even more impressive than that, because each of these 512s are single system image standalone production machines by themselves. And so each of these machines would come in typically on a Monday or something, and by Tuesday or by Thursday or Friday, they would be up and running actual NASA code. Truth be told, most of the applications still run on each of these 512s by themselves. There are few applications that are run across multiple boxes. There are at least 2 cores that have run on 4096 processors. And of course, we ran the LinPack benchmark, which is the benchmark that is used to rank all the supercomputers in the world. And LinPack ran at 52 teraflops, which put Colombia at the number 2 position in November 2004. We still believe that it is the fastest operational supercomputer in the sense that it's actually doing work. Right now, it's ranked 4th in the world. There's the 2 Blue Gene machines ahead of Colombia, and number 3 position is an ASCII Purple machine at Livermore. Right now, at any instant of time, we have about 150 or so simultaneous logins. There are 900 accounts, 160 projects running on the machine, and that sort of covers all kinds of applications. The next few slides sort of show you a little overview of what the architecture looks like, and Bob Ciotti is here also, and he can talk to you a little bit more in detail. So these are the 512 nodes. They're not all the same. As you can see, they're basically 3 kinds. They're the 3700s that are at the top. They're 1.5 gigahertz, 6 megabyte cache nodes. And then there are certain 512s that are 1.6 gigahertz, 9 megabyte cache, and then there are double densities so that there's more tightly packed together. They're all connected through several GIGI interconnects, which are used for more of the system side. Then there's the InfiniBand fabric, and then the 10 GIGI TCP/IP interconnect to connect all these up. Then there is also a front end, which is the 128 processor Altics that is called the channel here. And that is connected directly to the graphics array. And I'm not going to spend too much time on this, but when Chris talks about this, he'll tell you a little bit more about how we can do real-time visualization, sort of getting results of Colombia and visualizing them. And that is some of the things that we did for hurricane prediction last year. And he will show you more about that. And then finally, there is the storage. We have 440 terabytes of storage. These are RAID disks. And they're connected through these 2 128-port Brocade fiber channel and dates. And at this time, the problem that we have at Columbia is that the computational power is not really balanced with this RAID. We need much more storage to be able to sort of store and process all the data that's being generated. As you can imagine, like I've said, since NASA is a distributed agency, you can't have a fat node sitting somewhere. You must have fat pipes flowing into the node. And so there is this effort also to try to get high-speed access, high-bandwidth connectivity to Colombia from across the various centers. We are in that process of doing that. There's various issues with that in terms of what the backbone could be. There are several things that we're using at this time. The National Lambda Rail, which is a consortium of various industry as academic partners as well as other agencies. And then currently we have high-bandwidth connection between ARC and Ames and Goddard. There are other connections to JPL, but it also depends upon what the internal local loops are within each of these centers. But again, the primary focus for doing this is that you have end-to-end distributed data access to and from Colombia across the agency. And at the right, it gives you some numbers so that you can see that it makes a huge difference. If you want to transfer 1 terabyte of data at 5 gigabits per second, it only takes about 30 minutes, but it could take 500 hours at 5 megabits per second. So it's important that, that access to this machine is sort of high across the various centers. So the next maybe 5 minutes or so, I'll just give you an overview. We had debated about giving you a certain flavor of kind of applications that are going on. To really do justice to this, you would really need many of these application scientists to come out here and talk to you in depth about what those applications are. What I'm going to do as part of an overview, and we can, as follow-on seminars on this series, we can think about what we can do. But what I wanted to give you here is give you an overview of kind of applications that are running here, and Chris will also talk a little bit more about some of these applications, mainly from the visualization side, but also give you an idea. So the machine that you can understand is 20 of these 512s. It's a capability machine. As a strict definition of a term capability is that you're actually running large process account jobs across the machine. But in a sense, each of these 512s are also capability machines because each of them are 3 teraflop machines by themselves. And the fact that you have 20 of them and you run an application on 16 of them simultaneously doesn't necessarily make it into a capacity machine. But nevertheless, these are some of the applications that are going on now. For example, I'll talk some of these. Recently, we contributed to this New Horizons mission that you just heard about in the papers and in the news for a Pluto mission. We've been working on some of the return to flight stuff, which is the space shuttle main engine redesign and trying to understand the flaws in that. We'll talk about some of the earth sciences work. And then 4 of these nodes, like I said, are connected, or maybe I didn't say, but 4 of the nodes are connected to a more high bandwidth interconnect that allows you to have a 2048, more of a leadership class system that allows you to do more breakthrough problems, because it is, also has 4 terabytes of shared memory, so you can run large process account jobs on that. So the next few slides, I'll show you a little sampling of the various things that are going on. So this gives you an idea of the space shuttle program, the return to flight. And this was part of the work that was done in part of the investigation process of the Colombia accident. Normally, we run various calculations on various sort of models on this. We have lower fidelity models that are shown on the left, which are when you're solving the Euler equations. Doesn't have the boundary layers and the viscosity all in there. You can run more of the Navier-Stokes calculations that are shown in the second picture. There's a sort of an animation that shows the tile and where it could have hit the leading edge of the orbiter. The problem, of course, is that you have to build many of these models of this debris. They're not regular shaped stuff. They're various odd shapes, and no one had actually thought about that such a tile could have fallen off. So a lot of new work had to be done in terms of developing models. There are questions about impact velocities and locations, and we have scientists at Ames with cooperation with Johnson have developed both ballistic and probabilistic models. So those are shown at the top right over there to understand both which tiles could have fallen off, where they could have impacted, and what damage they could have caused. Work is also going on for that's external flow. This is for the space shuttle main engine. That's the picture of the space shuttle main engine. Gives you a little bit more close-up view, and Chris will show in his talk an animation of the complex airflow and the unsteady nature of the flow within the inducer in the pump, and how that causes backflow and causes vibration and fatigue and damage to the space shuttle flow liners. And again, this is required both for returning the shuttle to flight, as well as to understand what designs or redesign or re-engineering have to be done for future shuttle engine designs, as well as for CEV and CLV design. This is switching gears. This is more of cosmology and astrophysics. This is a mission that will go up in 2015. This is a collaboration between NASA and the European Space Agency. This is a laser interferometric space antenna. And the idea of this mission is to try to understand the origin of the universe and how this all started. So as you can see, there is a little picture over there. This is 3 spacecraft in a perfect equilateral triangle, arm length about 5 kilometers. And they will sort of follow the Earth. And there's a little animation here. They'll follow the Earth at 20 degrees behind the Earth and try to measure these very small vibrations in the gravitational waves that were formed during when massive black holes merged. This is an animation of massive black hole binaries merging. So they go through this in spiral stage, and then they go through this merger phase. And that is where you need to solve these full Einstein equations in 3D and as well as in time. Requires a lot of computational effort. And the idea of the simulations that are going on is to try to understand when the data comes back, you'd be able to model that and be able to sort of, scientists will be able to understand how universes were formed and galaxies happened. And again, like I said, I'm trying to show you a sort of a sampling of the various things that are going on. This is again from last year. This is hurricane prediction. This is from 2004, and we'll in the next part of the talk, we'll show you results from 2005. But this is Hurricane Ivan, which was in, I believe, September of 2004. The lower right picture shows you three tracks. So the blue track is what was originally predicted by the National Hurricane Center, and the other 2 tracks was what was predicted by this FBGCM code and the actual track of the hurricane. As you can see, there was huge discrepancies between what actually happened and what was predicted. In 2005, because of the work that happened in 2004, one of the codes that is used for hurricane prediction is run on Colombia 4 times a day, and then that would get sent to the University of Florida and get merged with other models. It's an ensemble model, so they would take various codes Some are good at predicting the track, some maybe at precipitation, wind speeds and all that. And that munched data would then get forwarded to the National Hurricane Center to make the predictions. The picture at the top shows you wind velocities, and everything below 100 kilometers per hour, I believe, are zapped out. So it's only color-coded by altitude and wind speed, and it shows you kind of the things that we are doing on Colombia, and some of the expertise that we have with visualization. And finally, I think this is my last slide. There is also a community effort to really predict climate and weather. And as you can imagine, the four major components are ocean and atmosphere, of course, those are the major components, but then sea ice and land. And this was one work that was done last year where we put together the ocean model and the sea ice model. And as soon as you try to put the sea ice model, if you use the latitude-longitude grid, then you have singularities at the poles. And so the scientists had to move over, as well as the visualization techniques, to move over to a cubic grid. And so this was a decadal run that was done on the Altix nodes. And scientists were able to see new features, things like vortices of the tip of South Africa that scientists had never seen before, as well as we developed new visualization techniques to be able to do these kinds of things. So I'll sort of stop there. If anyone has any specific questions or comments, I'll be happy to take those. And then, as you can imagine, there are many more of these things we can talk about. Any one of these could be a 45-minute talk by itself, and we can talk more about the details, about the science. Yes?
Can you say a little bit about the programming model for the machine?
So right now, since you think each of these 512s are single system image, you can write OpenMP code, for instance. Of course, naive OpenMP code is not going to scale up to that because of all the thread management overhead. But if you did it in a domain decomposition way, and we have examples of actual production code means codes that are more than 100,000 lines of code written in OpenMP running on a 512. Typically, people run it in a hybrid mode. So you would have an MPI plus an OpenMP mode. We also have developed a model called MLP, which instead of using the MPI calls, sort of leverages the shared memory architecture and uses Unix port processes to do the coarse-grained parallelism and then couple with the fine-grained OpenMP. If you want to run across boxes, of course, you have to run it in hybrid mode or at least pure MPI. And then people have also done nested OpenMP, for example. So you could also do like 3 levels of parallelization, MPI, and then nested OpenMP.
What's the point-to-point latency for MPI in that machine?
Bob, what is the point-to-point latency? Any other questions, comments, claims? Okay, so I'll turn this over to Chris, and Chris will give you a little overview of the visualization work and data analysis, and so I don't know how you want to do this.
All right, well, good start for the visualization talk. You can tell we're not Mac people. All right, so I'm representing the visualization group at the Supercomputing division at Ames. There's 5 people in the group, all of whom are here. So if there's any questions about any of this, we can get the appropriate person to answer that question. So what I want to do is just give a brief overview about the kinds of things that we do and some of the strategies that we employ to do those things. I don't have enough time to go into detail. Okay, more into the microphone. So I don't have enough time to really go into detail about anything, so I just want to give a broad overview, and then if there's interest in any of this, we can go into it either in the question period or at a later date. So basically what we do is scientific visualization, support research and development for projects running on NASA supercomputers. Primarily, that's physics simulations of all kinds, and Rupak showed some examples of that in his talk. The characteristics of the data that we see, they're large. Large today means on the order of terabytes. We're seeing data sets that are 10 terabytes, and bigger is coming soon. The domains that we see typically have a spatial interpretation. They're trying to model some chunk of the world, either very big or very small, or somewhere in between. And I point that out because a common distinction is made between scientific visualization and information visualization. And commonly that distinction is made on the basis of whether there's an inherent spatial attribute to the data or not. Most of our data is spatial. Commonly, but not always, the data represents some time-varying phenomenon. And so that means that we rely on animations quite a bit, the time-varying stuff. And the data, probably most of the data come from partial differential equation, evolution equations that are discretized onto some mesh system. We do see some data that are particle-based, for example, molecular dynamics data, and some other n-body simulations. Some of the astrophysicists and cosmologists use n-body simulations. So those are Lagrangian, they're not on a mesh. And some of the data we see comes from basis function models in some abstract space. For example, quantum chemistry calculations use some basis, plane waves or Gaussians in a configuration space. Our emphasis is on interactive graphics and exploratory analysis. And more it's necessary to visualize the data as they're being computed. And we refer to this as concurrent visualization. And that allows us to capture every time step of a lengthy integration without inordinate amounts of I/O. And finally, I'll say a little bit about our work in tile display systems. Okay, so generally we're application-driven. It's pretty obvious. And the model, our approach is basically we work in close collaboration with the scientists that are the domain scientists that are resorting to numerics. We work in an iterative fashion, but over the course of many of these iterations, we've tried to extract several generic components that we can reuse on the next go-around. And so the bulk of this talk will discuss 3 of these: our data model, the field model, our visualization technique library, VisTech, and our distributed framework, Growler. And like I just mentioned, I'll say a little bit about one of our display systems, the Hyperwall. Just to provide a little context, here's a very high-level view of the kinds of things that scientific visualization involves. In the center, I have a data source. This can be a running calculation, some files living in the file system, or maybe an instrument. And there's pretty much 3 things that we need to do. One, we have to, at the bottom, we pretty much have to get a handle on what the data are, how to interpret the bytes at the lowest level. Once we kind of have the data in hand, we can apply various transformation techniques. This is where the graphics comes in, where we translate floating point data into intermediate geometry and ultimately pixels. And then finally, we have typically the data source, the display systems, analysis module, and so forth aren't co-located, so we need to harness these things together. That's the upper right box, kind of controlling all these things, providing interactive environments and so forth. In magenta here, I have kind of these three things. If you're familiar with semiotics, study of signs, signs in the sense of signifying things, that's typically divided into three disciplines: syntax, the formal aspects of signs; semantics, the meaning or what they represent; and pragmatics, or use. And it's a fairly abstract way of viewing visualization, but I think it's a pretty close match. And in blue, you can see the three FM, VisTech, and Growler, the three kind of reusable components, and then also the Hyperwall and where they live in this abstract view. So just to motivate things, here's an example. Here's a typical data set we might see. This is part of the fuel injection system of the shuttle. So on the left, this big pipe coming down, this is the pipe that delivers liquid hydrogen from the external tank. This is the giant tank that the shuttle is bolted onto when it lifts off. It's about 16 inches across, just to give you some scale. And that brings the liquid hydrogen down. It trifurcates, and each one of those three subpipes feeds one of the engines. And at the end of each one, and we have one of them surrounded in a box, there's a relatively low-speed impeller. There's a close-up on the right, and that moves the fuel into a high-speed turbine that actually blows it into the engine. Okay, so this data set consists of 264 zones or submeshes. So the whole space, including this complex geometry, is discretized into these kind of lattices. In this case, they're structured meshes. And these meshes are kind of warped and wrapped around the geometry, and they overlap and basically fill all space, but they can't be warped too much or the numerics break down. So we get this pile of meshes with a bunch of flow primitives assigned to each node, and we want to do something like this. So here's a typical animation that we'll do. The one major point of this study was to try to understand the causes of cracks that are seen in these two rings of holes. These are actually ports that are put into this flow liner to retrieve welding debris after the joint is formed. So they're not, or they initially weren't designed with flow in mind. But in use, the liquid hydrogen actually flows in both directions, it turns out, through these holes. The color coding you see, what we're doing here is seeding particles into the flow and advecting them. These are massless particles, so they're showing the direction of the flow. The flow is, now it's away from us, it's toward that impeller. The blue color signifies flow in the correct direction, it's going downstream, and red signifies backflow. And when it turns, so in general you can see that the flow, the impeller kind of pulls the flow forward and in. And you can see around the outside we get reverse flow. And in general terms what's happening is that the flow has a lot of momentum and it's actually kind of bouncing back off the outsides of the blades. You can see these reverse flow in these pods around the outside. And what that gives rise to is a kind of back and forth motion and a resultant pressure fluctuation around these holes. And that was fatiguing the metal. And in some cases that was even leading to cracks. Okay, so we want to create this visualization, and we're given this giant pile of mesh data. So how do we do it? Okay, so the first thing I want to talk about is our data model. And this pretty much summarizes what it does. The data model is called the field model, or FM, and it basically gives us a uniform abstract interface to underlying discrete data. It allows us to treat the entire computational domain as a continuous field, and we can ask for values, either primitive values or values that are derived from the primitive quantities at arbitrary locations. And the library does all the dirty work of figuring out what submesh, the physical point we're asking for, corresponds to, what cell in that submesh contains the point, pulls all the values at the vertices of the cell, does the appropriate interpolation and perhaps derivation from the primitive quantities to the derived quantities that we want. And along the way, we can run the values through various filters. For example, differential operators, we might want the gradient of some scalar quantity or the curl of a vector quantity and so forth. And the really nice thing about this is that it kind of is able to provide the same API for a number of underlying mesh types. And we see a lot of different kind of mesh types. In the example I showed, it's overset curvilinear meshes. It's a whole bunch of curvilinear meshes filling space, but we might see tetrahedral meshes, which are unstructured, and various other kinds of discretization schemes. I want to briefly mention a few optimizations we put into this interface. One is to exploit symmetries. Frequently, and in this case, this running example, the entire collection of meshes will be transformed versions of a smaller set of what we call reference meshes. So we will actually only load into memory the set of reference meshes and then generate the entire set of meshes through applying the various transformations. This greatly lessens the memory load and the I/O. And this benefit is especially prominent in time series. So we can load the set of reference meshes for the first time step, and then use that for all subsequent time steps, and get even a bigger win. A second optimization is paging. So many visualization techniques will only touch a small amount of the data. So in this example, we're doing particle tracing. We're trying to show the path of one massless particle released from one of these ports. And you'll notice it only passes through a very, very small volumetric fraction of the data. We don't need to pull data from the other side of this ring in order to advect this particle. So what we do is bring in the data we needed in page-sized chunks and then maintain a working set of those cached pages. And this also works remotely. It works over the network, which allows us to just pull the data over the network that we need for a particular visualization technique. I mentioned earlier that we also support derived fields. So typical computational fluid dynamics will calculate a momentum variable and two thermodynamic state variables. There's lots of other variables that scientists are interested in, for example, pressure or temperature. These are all derived quantities. So you have to pull the appropriate primitive variables and then run them through a transformation formula, and we'll only do that where needed. We won't frequently, many data stream or data flow utilities will actually calculate these derived quantities across the whole domain just in case you need them somewhere. We'll only do that where needed. This is an example of a derived field. Pressure, it's actually a function of E is energy, M is momentum, and D is density in the expression. And so we can define this quantity. In this case, this is a Python front end that allows us to type in these formulas on the fly. This actually doesn't evaluate anything anywhere. It just creates this virtual little derived field machine that gets invoked when and where needed, depending on what the visualization technique requests. Okay, so that's our field model. Once we have the data in hand using the field model, we want to apply a number of different visualization techniques. This is just a laundry list of some of the visualization techniques that we've encapsulated into a library interface. And there's basically four big groups here. Sometimes we want to visualize the mesh itself, the geometry of the mesh. And then most commonly we get scalar and vector fields defined on those meshes. We see some data that are tensor data, and I don't have those listed here. And then there's kind of more abstract techniques that I have under this heading of feature detection. We might want to find features like vortex cores, that's especially of interest to the fluid dynamicists, separation and attachment lines, and various topological features of the field. So I'm basically just going to show a bunch of examples of this, of the viz techniques. Here's a standard scalar field technique. This is showing pressure on the surface of the shuttle in the ascent configuration, just mapped onto a simple rainbow color map. This is from a simulation of the dynamics of the solar atmosphere. This is showing current sheets in the magnetic field as a scalar technique, and then also showing some of the magnetic field lines. Simple vector field technique. Here's an animation showing large-scale structure evolution in the early universe. The ticking number in the lower left is billions of years before present. So the simulation starts at about 13.5 billion years. That's a redshift of about 1,200. And what you're seeing, the domain here is about 500 million light years across. And it starts with almost a uniform distribution of matter, in this case non-baryonic dark matter. There's slight fluctuations from uniformity that are given by the cosmic microwave background statistics. And then the only force that non-baryonic dark matter feels is gravity. So all the structure you see developing here is purely a result of attractive forces. And you see the structure resolve into these sheets and filaments and kind of dense clots. This is very close to what we see from the deep sky surveys today. And just for some scale, one of the kind of medium-sized yellow blobs there is a cluster of galaxies that might contain somewhere between 100 or 1,000 galaxies, like the Milky Way. So this is a N-body, a particle-based simulation technique, and actually a particle-based rendering technique, by the way. Okay, this is showing surface winds on the Earth, obviously. So this is from a 5-day forecast of hurricanes. This is actually from 2004. This is Hurricane Francis crossing Florida just now. You can also see at the same time, this is looping, there's significant typhoon. This is Typhoon Songda. It's happening at the same time. And you can see various fronts kind of at the low and high latitudes. This is using a technique called LIC, or line integral convolution, which basically combs a noise field with the flow field. So the high frequency modulations you're seeing here, the kind of moving streaks, are showing the direction of the flow. The low frequency modulation, the kind of bright white areas and the not so white areas, that's proportional to velocity magnitude. So you can see that the big cyclonic motions are quite a bit faster, and there's kind of some doldrums down the equator and so forth. You can also see, by the way, if you look across the land, across South America in particular, you can see this kind of right to left wave. That's the terminator, that's morning, kind of coming across, and you can get you see some afternoon convective activity, the thunderstorms over the Amazon basin and so forth. Okay, many visualization techniques we like to think of as queries, and they're commonly location queries. You want to know what's going on at a particular location in a computational domain. There's another kind of query, which are condition queries, and what you want to know is where in the domain certain conditions obtain. And so many of our feature detection algorithms can be thought of profitably as condition queries. We've developed many of them for CFD, for computational fluid dynamics. For example, those that are designed to find flow reversals, wakes, shocks, various topological features of vector fields like critical points, critical lines, critical surfaces, vortex cores, and so forth. But we found that these techniques are generally and usefully applicable to many different kinds of vector and scalar fields. For example, we've applied our vortex core finder to neural map data. And found some very interesting features. I'll show one example. Feature detection. This is showing the results of our vortex core finder. The vortex cores are actually the white lines. Just a little bit of noise. This is showing flow over a Harrier jet. And the main vortex is actually down by the tail, and they're actually seeing buffeting by this vortex against the tail, which is why they're doing this, partly why they're doing this investigation. Locating that vortex core guides us in the placement of seeding the particles for the particle tracing method here. And in particular, that yellow trajectory that you see coming from upstream, you can see it almost goes under the tail, gets recirculated back over the tail, almost escapes out the back, gets pulled into the vortex, spirals in, and then the red trajectory is actually it leaving the vortex core. You see it's a very, very complex flow. Okay, so that's visualization techniques. So the third component I want to describe is our distributed component framework. The motivation is that our data sources, our compute engines, and our display devices and environments are typically not co-located. So we need to functionally rig them together. There's very rich functional interfaces. So in order to do this, we need a means of expressing rich communication semantics. We have to deal with the fact that the different components that we're wiring together have very different characteristic timescales. And what I mean by that can be illustrated by an example in the lower right. There's a picture, a kind of mocked up picture of an environment we've created for computational steering and interaction with a molecular dynamics simulation. So this allows you to kind of push atoms around while the molecular dynamics are running and get an idea of how they behave. And we have that rigged up with head-tracked stereo glasses and a haptic, a force feedback device, and so forth. The molecular dynamics simulation behind this might be updating the atomic positions and velocities at a small number of times a second, 1 to 10 hertz, say. The stereo glasses need to be refreshed at 120 hertz, 60 for each eye. The hand tracking, which allows you to grab an atom or a group of atoms and move them around, you need to give kind of reasonably snappy feedback to the user, or you lose the interactive or the immersive environment. That needs to be updated at least 10 hertz. And the haptic device, the force feedback device, has to be updated at 1 kilohertz. Turns out that's about flicker fusion frequency for touch. If it's updated any slower than that, you feel it as kind of a buzzing instead of a solid force. So we have to couple and integrate all these different event loops which are running at different times. So we have to interleave these things and be clever about that. And that's in part what this, our framework is designed to support. And of course, all this stuff is happening over the network, so we have to deal with failures of the network, security issues, and so forth. So I'm just going to give this one slide a list of features that our framework has. In my backup slides, I can kind of go into more detail about any of these if there's interest. So first of all, we have our own interface definition language that allows us to express these complex functional interfaces. It's very C++ centric. Basically allows us to work in the same classes that we use in our local applications. We have an RMI, or remote method invocation service. This allows us to make method or function calls on remote objects. Those remote objects are reference counted, so when their reference count goes to 0, they're cleaned up. It helps immensely in resource management. Many of our distributed systems rely crucially on events. So typically, these events have large data payloads. These are typically updates from a running simulation. That's a very common case. And when those events show up, you need to intercalate them into your interactive graphics loop. That's a common situation. And so we have a very sophisticated signal selector mechanism that allows us to assign the incoming data to a thread for maybe some local processing. Maybe it generates a graphics display list, and then at the last minute, that's handed off to the thread that's servicing the interactive user interface. And a lot of that handoff mechanism relies on read-write buffers, which were developed in the group to kind of help the synchronization and to minimize data copying. And then finally, all of this machinery allows us to kind of create this distributed component framework. We need to manage that. And so the namespace, we have a distributed namespace that basically we can publish interfaces that are available and then hook them together on demand. So this functionality allows us to create something like this. I don't expect you to be able to read this, but it gives you an idea of the complexity of the visualization pipeline we set up this year for the hurricane forecasting effort. And so using this system, we're actually able to interface with a hurricane forecast running live. And as Rupak mentioned, these were running 4 times a day in production mode every day during the Atlantic hurricane season. So from June through November. It was actually extended this year into December for a couple weeks. And as the simulation is running, we reach in and through the shared memory of the Altics, we're able to copy out the data that we're interested in them, move that over the InfiniBand to the front end of Colombia, send that over Ethernet down to our rendering engines, generate frames, encode those as MPEGs, and then stream those wherever we want, including back to Goddard, where NASA Goddard, the center at which this code is being primarily developed. Here's an example of one of the 5-day forecasts. And this actually shows Hurricane Rita. You can see it in the Gulf. It's just taking landfall now. And you can see that in this global view, this is a global model, that these hurricanes, as big and as destructive as they are, they're actually only a minor feature in the whole global circulation. And they're being pushed around by these very, very large-scale dynamics. Gives you an idea of the scale of the difficulty of the prediction problem. Okay, using our framework, we've also rigged a live interface to Colombia itself. I'm hoping I'll be able to connect to that right now. Let's see if it works. Okay, it appears to have gone to sleep, so probably our SSH tunnels have timed out. We can fire that up after the talk. But you can see the static version here. We basically have 3 views of each of the 512 nodes on Colombia. So the kind of upper left, this tiled section, that's showing the 512 processors, and it's color-coded by their state of activity. The red lines show memory usage used in free pages. And the kind of graph, the network graph, shows the interconnect, the topology of each of the 512s, and shows activity on that. I apologize for that timing out. Let's go back. Okay, and finally I want to just show a few slides about our tile display system we call the Hyperwall. It's a 7x7 array of flat panel displays. It gives us about 65 million pixels over about 55 square feet of viewing surface. So we can run this in several modes. One of them is standard Powerwall mode, where we show a single large image, like this Modus composite. More interesting is to use the separate displays to show parameterized layouts of related images. So here we're showing the design of a Mars airplane, and in this case it's laid out by airspeed left to right and attitude up and down. So this shows a lot of different flight conditions, and you can compare them side by side. You can interact, you can kind of roll these around, just like your standard desktop 3D viewer, but now you're interacting with the whole set that's laid out in a systematic fashion. And another mode is to have visualization and analysis utilities that are functionally interconnected. So in this case, we have a bunch of linked scatter plots, these gray blobs, and they're actually linked to a bunch of 3D point plots and volume renderings. So this allows you to do things like select a range of points on one of the displays and have that update in all the others. So this allows you to probe high-dimensional dependencies and so forth. Here's a little more readable version of that. In the upper right, you can see this is a data set. This is a section through an airfoil. And so there's a mesh wrapped around this airfoil, and the flow Navier-Stokes equations are being solved on that mesh. So at each point in that mesh, there's a whole bunch of other variables, like velocities, pressures, entropies, and so forth. So we can take that mesh and actually embed it in these other spaces. So for example, in the lower left, we've embedded it in velocity component space. The free stream, or the undisturbed flow in this data set, maps to a single point here on the x-axis. Everything else is a perturbation of this flow caused by the wing. So regions of the flow farther away from the origin, which is here, are accelerated flow, and so we can select a range of those with this blue annulus tool, and you can see those correspond to the top of the wing. And flow, which is slower relative to the free stream, is in green. You can see that's below the wing. You can actually see in this pressure versus temperature plot that low speed is high pressure and high speed is low pressure, so this is kind of visualization of lift and so forth. You can see all sorts of other features too, these little kind of wing-like things. This corresponds to this flow reversal here, and so forth. So this is an example of kind of a visual representation of condition queries, and we can composite these arbitrarily using Boolean expressions and so forth. So this is my last slide. The group just wrote down a few interests and challenges that we thought might be relevant to the folks around here pertaining to metadata. You can read these, but the gist of it is that we deal with a lot of large binary objects. We extract a lot of data around them, and we want to kind of retain that data and be able to attach it to these objects and search over it. And we'd be very receptive to any assistance on that front. So I'll stop there. I'll take any questions, and I guess we're supposed to go into discussion.
So you guys thinking about making essentially an ontology of all the different variables that you have and how they can be related to one another and what visualization tools work on what and stuff like that? Is this a valid goal for you guys?
Feel free to chime in, other people in the group. I'm not sure how realistic that is.
Okay.
I mean, like I mentioned at the outset, we're very demand-driven. So the scientists typically have very specific questions that they want to get at. Internally, we might conceivably construct and rely on that kind of things. That's probably too general for most of the stuff we see. Other people on the team might disagree.
How do you debug these systems? I mean, it looks very complex, and I'm sure, I mean, it's not clear what the output should be, so I was wondering what your thoughts are on that.
Well, it's fairly modular, so we kind of debug it piece by piece. Don't know what to say beyond that. It's the usual divide and conquer. And, typically, the failures we see are typically in the large distributed systems are failures of integration. So one part will drop out, and the whole thing will kind of either just die or limp along.